Živijo, pozdravljeni in pozdravljene v novi epizodi podcasta Temna stran Lune, kjer vsak mesec predstaviva temo povezano z astronomijo in vesoljem.
In tokratno temo, dajva reči, sva izbrali, ker je bila nekako povezana z novicami, o katerih smo slišali februarja meseca. Takrat sva brali o tem, da naj bi asteroid v bodoči prihodnosti mogoče trčil v Zemljo, in takrat je bila zelo aktualna ta novica.
Ja, sicer verjetno ste tudi sami opazili, da je takih novic kar precej, na vsake toliko se pojavi kakšna v medijih, ampak zaenkrat še ni nič takega večjega trčilo v zadnjem času.
Ampak istočasno se nama je zdela tema zanimiva, mogoče iz širšega vidika. Zato, ker je res tudi, da včasih prebiramo o tem, kako se raziskovanje sedaj napreduje, torej pri samem raziskovanju asteroidov, ne. Namreč niso več samo oddaljeni objekti, ki jih lahko pač pregledujemo na nekih slikah, ampak gre za take objekte, do katerih lahko tudi pridemo in se celo vrnemo nazaj.
Ja, točno. Verjetno se spomnite iz novic pred nekaj časa nazaj o misijah, ki v angleščini jim rečemo sample return missions, oziroma v slovenščini misije, ki nazaj na Zemljo prinesejo vzorce. Se pravi, poletijo do kometa ali pa asteroida, tam zajamejo vzorci in potem se vrnejo na Zemljo. No, in pred časom sem imela srečo in priložnost na Inštitutu za astrofiziko na Kanarskih otokih, kjer tudi sama delam. Sem imela priložnost spoznati eno raziskovalko, Tanjo Le Pivert-Jolivet, in ona se ukvarja ravno s tem. In to nama je zdelo zelo, zelo zanimivo, in zato smo jo povabili v goste. Tania Le Pivert-Jolivet is an expert planetologist. She's working with the primitive asteroids in the solar system, and she's analyzing their spectra to understand what they're made of and how they evolved. She's also connecting this knowledge with the results from the sample return missions. These are samples that were brought to Earth from space missions. She obtained her PhD in Orsay, France, and currently she's a postdoctoral researcher here at the Institute of Astrophysics of the Canary Islands. Tania, welcome to our podcast.
Thank you for inviting me. It's a pleasure to be here with you.
Let's start. So, as I mentioned, you study asteroids to understand the past of our solar system. Can you tell us a bit about how did you become an astrophysicist and how did you decide to study primitive asteroids and small bodies of our solar system?
Well, I think that my interest for primitive asteroids started when I was in high school. When I was a child, I was not super interested in astronomy. It really started in high school. At that time, I didn't really know what to do with my future. But I had a teacher, a biology teacher, that was, she really loved geology in general, and she was super interesting. She taught us many things about meteorites, the fact they could be the building blocks of life. And at that time, I was really naive. I didn't know really to expect. I was thinking of maybe there is like living organism in meteorites, and one day we will find them and we will find that life is in the meteorites. Of course, it's totally far from the truth. However, this highly stuck in my mind and during my studies after the high school. And yeah, little by little, I tried through my internships, through my studies to go in that branch of astrophysics.
Oh, that's a very beautiful story about the role model that your teacher played.
Teacher play an important role in convincing students to do some studies.
And what about today? Can you tell us a little about what do you do today?
I am, as you introduced, I am a planetary scientist. So I study the objects of the solar system. And I try to understand the history of the solar system, basically, since its formation. And for that, there are several ways to understand the history of the solar system. And one of those ways is to study the asteroids. So asteroids are small bodies. in the solar system. They are smaller than planets. And most of them are orbiting between Mars and Jupiter in an area we call the main belt. And what is interesting about those objects is that they are the remnants of the early formation of the solar system that started 4.6 billion years ago. And they did not evolve as much as planets. So they give us valuable information to study the different steps of the planetary formation. I like to use the analogy of the archaeologists who study objects from the past, artifacts, in order to understand the evolution of a civilization, for example. It's the same idea, but the scale is the scale of the solar system. And me, in my work, I'm interested particularly in primitive asteroids. They form far away in the protoplanetary disk, and we think they accreted ices and organics. And this is important because they might have provided those elements to the inner solar system and to the Earth. So this is why we scientists are interested in primitive asteroids in particular.
They migrated from the outer parts to inner parts. This is how they delivered some organics, as is mentioned, to the inner system.
Actually, the formation model, the dynamic model, shows that at some point the giant planets, when they grew up, they migrated inwards. And this had a consequence on the orbit of the smaller objects. A lot of them were thrown away from the solar system, but some of them were implanted in the inner solar system. And we also think that this is how the asteroid main belt was created, by implanting objects that were far away and also closer to the sun through the migration of giant planets. At least this is the theory that explains the most of the things we see today in the solar system.
Since you mentioned before that you were attracted by the work of your teacher, so also my almost 10-year-old son was asking me or explaining me something how the water came to Earth, no? And he was citing impacts of asteroids as one of the main bodies that carried water. So what do we know really about how the Earth became a planet full of water, and why does, for example, the moon not have water oceans?
Okay, so concerning the origin of water on Earth, it's still debated. We still don't really know. There are several theories to explain that, and one of them involves the asteroids. So this theory is based on the fact that the rocky planetesimals, which will become rocky planets after, they form close to the sun. And close to the sun, the temperature was very high. So the water could not condense in the form of ice, and it could not be accreted by those rocky planetesimals. But when you go far away in the protoplanetary disk, after a certain limit, the temperature is low enough to enable the condensation of ice. This is what we call the snow line. And beyond this limit, the water ice could be accreted by the planetesimals. And we think that the primitive asteroids were formed beyond this limit. So they could have accreted this ice. And then we know from the dynamical study that those objects from far away in the solar system were at some point implanted in the inner solar system. So they are a very good source of water for the inner solar system. This is a likely scenario. But it's not the only one. And there are a lot of debates about the origin of Earth. And concerning the moon does not have water ocean as its surface, basically because it's too small. So the planet cannot hold an atmosphere like the Earth. And the magnetic field also is very weak. So the issue with the moon is that because of the absence of atmosphere, you have very strong variation of the temperature at the surface. and this is not. It makes it difficult for the moon to hold liquid water molecules at the surface. But in some regions of the moon that are never illuminated, for example at the poles, we know that there is some water in the form of ice. There are some frost, water frost on the poles of the moon because there is no illumination, so the water can condense here.
Let's make it clear from the very beginning. So I wonder, what's the difference between an asteroid and a comet? For example, we all remember that there was a comet chased by a Rosetta mission. It was like a duck-like object. It was probably a result of a collision between two minor bodies. So what's the difference between comets and asteroids? And then also asteroids, can they also, for example, two of them, can they merge together, like in the case of this comet that was chased by the Rosetta, or what? Can this happen?
So yeah, indeed, there are differences between comets and asteroids. The main difference is that comets contains more ices, and asteroids contain basically no ice. And the comets, they have an orbit that comes closer to the sun. So when a comet approaches the sun, there is a sublimation of the ice and the dust on the comet. And this is when we can see a coma around the comet and also the tail of the comet. However, in the asteroid main belt, we can observe asteroids which show an activity related to the sublimation of ice, just like comets. But they are asteroids with a typical trajectory of an asteroid, but they are active. So the boundary between the two is not completely clear. And concerning the formation process of asteroids and comets, when you have a body like this, that is like the duck shape of 67P, we think it's a sticky collision that could have formed this. We have some asteroids which show a shape of possible collision, but at the beginning, we think that the planetesimals, so not the asteroid we can find today, but the planetesimals that form in the early stages of the solar system, formed by accretion of many small materials. And it grew up like this. And then for the asteroids, the history is very complex because the planetesimals, once it reaches its maximum size of a few kilometers or maybe more, maybe 10 or 100 kilometers, then it will be fragmented due to collisions. And some of the fragments will reaccrete to form smaller and smaller asteroids. And like that, you can have different generations of asteroids. This is how asteroids form, basically.
Is there any difference in size, for example? How big are comets and how big are asteroids?
That's a good question. Asteroids, I mean, you have asteroids of all types of sizes and shapes. But for example, you won't find any comet that has the size of Ceres, for example. Yeah. And also another difference is the origin. So the asteroids are mainly in the main belt, and the comets come from far away. Some comes from the Kuiper belt, and other from the Oort cloud that is very far away, than it's like the limits of the solar system. It's beyond the limit of the solar system.
So they have very different origin. They're different objects.
They have different origin, but it is true that some comets, they can at some point be implanted in the asteroid main belt and act like asteroids, having an asteroid trajectory, but still showing some activities. So even if a lot of comets and asteroids are very different, some of them share similarities.
And we mentioned that you are also studying samples that are taken from asteroids and brought back to Earth. What are the main questions about asteroids that astronomers like you are trying to answer with these studies? So studying really the samples from asteroids.
The key questions we want to answer are first to understand what was the initial composition of the solar system. And for that, it's important to study the primitive asteroids because they give us insights on the composition of the object who formed beyond the snow line. So this is the first thing. And then we want to understand how this initial composition evolved, how the primitive planetesimals evolve chemically, but also dynamically. So, for example, we want to understand how the composition of the primitive planetesimals evolved since its accretion. We know that given their size, the largest objects, they heated due to the presence of radioactive elements inside the bodies. And this, the temperature of the bodies increased. So the ice they accreted melts. It interacted with the other rocks in the planetesimals to form new hydrated minerals, like phyllosilicates, for example. This is something, the phyllosilicates are layer minerals like clay we can find in meteorites and also in the samples from the sample return mission. So the idea to understand how this process, aqueous alteration, modified the initial composition of the planetesimals. Also, the aqueous alteration created new complex organic molecules. So we want to understand what type of organic molecules, what are the chemical reactions who lead to that. And we also want to understand the dynamic evolution of the planetesimals. How can we pass from planetesimal that have a size of several tens of kilometers to smaller asteroids? And why do they move from the outer region of the solar system to the main belt and to the near-Earth asteroid region? Because the asteroid I studied is a near-Earth asteroid, so today it's orbiting close to the Earth. It's not in the outer solar system anymore.
Mm-hmm. So you already mentioned some of the results, but so what's in your opinion? What are the main results, or what are the most important advancements in knowledge that we got from all these studies in the past? Or how did sample return missions improve this, or how did it help?
Okay, so before the sample return mission, we already had some primitive samples in our laboratories because we have some meteorites in our collection that fall on Earth and they come from asteroids. Some of them are primitive meteorites. We call them carbonaceous chondrites because they contain organics in different proportions. And by studying these meteorites, we could already know a lot of things about the primitive objects in the solar system. However, the issue is that the carbonaceous chondrites we don't have a lot of them in our collection. First, because they are very fragile due to their composition, and probably most of them are destroyed when they enter the atmosphere before falling. Moreover, even if we have the meteorites, it's really difficult to make the link between a meteorite and its parent body because basically it falls without any context. We don't know where they come from. So there are a lot of work that tries to link the meteorites with the asteroids based on spectroscopy, because spectroscopy is a technique we can apply in the laboratory on meteorites and at the same time on remote sensing observation of asteroids. However, the link is very difficult to make, mostly because in the visible, for example, when we do spectra in the visible, many of the primitive asteroids don't show spectral bands, so it's really difficult to do those things. And then another issue is that the carbonaceous chondrites, when they are on Earth, they can be subject to terrestrial contamination. They stayed on the ground for many years. In the museum, they are not protected the best way possible. So all of that changes their composition. So it's really difficult to say if the organics molecule we find in a meteorite are from terrestrial or extraterrestrial origin. And this is why it's important to do sample return mission to overcome those two issues. The first one is that we know exactly from what objects the primitive samples come from. And the second one is we know that the samples are not contaminated. So we can ensure that the things we see in the samples are very representative of the asteroid.
Mm-hmm.
And this is why the two sample return mission really helped us by understanding, for understanding the evolution of the solar system and all the questions I listed before.
Two of such missions were the OSIRIS-REx NASA mission, right? And the other one was Hayabusa 2, a Japanese mission, I believe. And how successful were they in bringing back the samples to Earth? So how much material did they bring, and did everything go as was planned at the beginning?
So I would say that the two missions were very successful since they brought back some samples. So it was the aim of the mission. The main challenge for this kind of mission was, of course, to do the sample collection. It's not only a spacecraft that is orbiting around an asteroid, taking pictures, doing measurements, spectroscopy, and then the mission ends. They need to collect samples and bring them back to Earth. And this was the challenging part. I wouldn't say that everything went as planned, because in planetary science mission, you always discover new things. The main challenge was probably the surface aspect, because before the mission, when astronomers did remote sensing observation of the objects, they measured the thermal emission. And from that thermal emission, they said probably the surface contains very small particles, a bit like what we see on the moon, some regolites, we call that. However, when we arrived at the asteroid, it was not fine particle at all. It was boulders, centimeter-sized boulders to meter-sized boulders. And it's very difficult for a spacecraft to approach this surface and to find a good collection sites. So I will say that the main issue was to find collection sites that are safe enough for the spacecraft, but also interesting in terms of science. But the two missions succeeded. The Hayabusa 2 spacecraft collected samples 2 times. And in total, it brought back 5 grams of primitive materials from the asteroid Ryugu. And the OSIRIS-REx mission collected samples 1 time, but since the sample collection system was a bit different, they could collect more samples, and they brought back 120 grams of samples from asteroid Bennu on Earth.
It looks very, very impressive. But on the other hand, when you say numbers, for example, 5 grams, it doesn't sound much, at least to me.
Yes.
It doesn't sound much, it's true, but that's enough to do the science we wanted to do. To give a comparison, before the Hayabusa 2 mission, the Japanese Space Agency had a bit of experience in sample return mission with the Hayabusa mission. And this Hayabusa mission was also a sample return mission, but not toward the primitive asteroid, toward S-type asteroid. S-type asteroids are asteroids that contains mainly silicates. This is why we call them S-types. And it was like the first attempt before Hayabusa 2. They had a lot of issues with the collection system, the capsule. When the capsule came back to Earth, they had also some issues to protect the samples from the atmosphere. And at the end, they could only bring back a bit more than 1,000 particles. And only with that, they were able to do some amazing science. So 5 grams is amazing for us. And 100 grams also, of course.
Yeah, of course. Yeah, now I see with this comparison that it's a lot, but still, these samples need to be taken care of very with caution, and they need to be careful not to contaminate them and so on. So, can you tell us how does a typical analysis look like? For example, yeah, how to avoid contamination, and I don't know, are there any other things that are important to take into account?
So yeah, the samples, since they return, I'm going to talk about the samples from Ryugu because I'm more familiar with it, but for Osiris-Rex samples, it's very similar. So since the return of the Hayabusa 2 capsule, the samples are stored in a clean chamber in a complex called the Curation Facility in Japan. And they are kept in a nitrogen atmosphere to avoid any contamination by the terrestrial atmosphere. For example, we don't want water molecules from the atmosphere to interact with the samples.
Mm-hmm.
So this is the curation facility. The aim of this complex is really to preserve the sample. However, there is no typical sample analysis, but it is true that the samples are very precious. So in the curation facility, since the philosophy is to preserve the integrity of the samples, only non-destructive and non-invasive techniques are used to characterize the samples. For example, we can use spectroscopy or photometry since we are just studying how the light is reflected by these objects. What does it tell us about the composition? But we won't touch the samples. But then if you want to know the exact composition of the organics molecules in the samples, you need to extract the organic matter. You need to damage, to destroy the sample. So if you want more precise information, the samples need to be destroyed. You have no choice.
Yeah, it makes sense. We want to preserve this. It was a lot of effort, a lot of money, a lot of time to bring this to Earth.
Since you mentioned those samples that are stored in the laboratory, did you get the chance to see it yourself in a lab or work on it?
Yeah, indeed, I had the chance to work with those samples. It was my PhD project. I was working with an instrument that is an infrared microscope. So it takes pictures of the samples at different wavelengths. And then we build a cube containing the images of the sample at the different wavelengths. So for every pixel of our cube, we have access to the spectra. So this is very interesting to study the spectra of the samples and also the spectral variation at the surface of one Ryugu grain. This analysis was done in the curation facility I was mentioning before. It's not the only type of instrument that is installed, but it's one of them. And I was working with this instrument. I was not doing the measurement directly in Japan, but inside the curation facility, our Japanese colleagues every day were measuring several grains. It takes a lot of time, basically, because we want to measure the grain with every angle possible. So it can take a lot of time. And I was, for example, I was connecting remotely to discuss the protocol with them. For example, if we see some interesting inclusion, we could decide to do another measurement of a certain field of view where we see this inclusion, for example. But so this work was done remotely. Then I was analyzing all the data because it's also a lot of data. And I had the opportunity to go once to Japan to visit the curation facility. So it's to enter there, you need to have the full suit to be. It's like a super clean room, so you cannot enter with normal clothes. You have to put something on top of it. And I could see the instrument, the chamber, the samples in the chamber, because you have some transparent windows to see the samples. And I think that the thing that struck me the most impressive thing was the aspect of the samples, because they are super, super dark. They are darker than coal, for example. Because coal, you can see it has some bright inclusions on its surface. Those grains were super, super dark, and it was really impressive too. At some conferences, I remember that at some conferences of planetary science, one of the Japanese colleagues was bringing around some Ryugu samples willing to show him to every scientist. And they were like, wow, it's amazing.
Yeah, very precious.
I think they will distribute some samples for outreach. For example, samples that have been exposed for analysis, they might give them to museums or to schools for outreach.
Wow, would be very interesting, to see. But I also wanted to mention here that, we all in the past years we heard in the news, this sample return mission brought back this material from this asteroid, this comet, and so on. And now it's so exciting to hear first-hand experience from somebody who actually saw this. It's wow, very. I wonder. So I think you mentioned before, but just to be clear about the age. So how old is this material you're studying in these asteroids?
That's a more complicated question than you can think.
Okay.
Because there is not one age of Ryugu samples, basically. Because as I mentioned at the beginning of the presentation, the planetesimals from which Ryugu originates, it formed a few million years after the birth of the solar system. So the material we are analyzing, basically they formed at that time. However, on the planetesimals, there was this process called aqueous saturation. So new minerals were created during several million years. Thus, they are a bit younger than the previous minerals. And then we know that the planetesimal, the parent body of Ryugu fragmented. Maybe there was different episodes of fragmentation and reaccumulation, leading to the formation of younger and younger generations of asteroids. And we think that the last disruption, the disruption that led to the formation of Ryugu, happened more or less 1 billion years ago. So depending on what you want to study, the age, Ryugu contains materials that were formed at different ages. But this is also something very interesting, because with one single asteroid, we can study different steps of the solar system formation that happen at different time in the solar system history. So this is also very interesting to understand.
So what you're saying is that Ryugu as asteroid is younger than its composition.
Yeah, the asteroid Ryugu we know today is very young compared to the materials that are inside it.
And so since you mentioned also the beginning, the protoplanetary disk and the planetesimals, can you explain us how did they form and how are they linked to our sun and our solar system?
Well, the story of the formation of the solar system is not completely understood. There are a lot of steps we don't understand, but basically, at the beginning, you have nebula of gas and dust. and the dust start to stick together. They become bigger and bigger. And then there are a lot of steps we don't understand, because at some point the sticking is not efficient enough. It should not be able to produce larger objects. However, larger objects were produced. But in any case, to do a quick description without so much details, because the details are debated, let's say that it's an accumulation due to gravitational attraction that created larger and larger bodies. And then the disk dissipated, and you have these planetesimals that will continue to grow through collisions, and later the giant planets migrated. So you had also a dynamic evolution of those asteroid and planetesimals. They moved a lot in the solar system, and this is also something that we don't completely understand. We think that there was some migration of the giant planets that led to the moving of a lot of smaller objects. But when this migration happened, this is really debated. We don't exactly know. We know it happened early in the history of the solar system, but there are a lot of different dynamical studies that gives different results. So there are a lot of things to understand about the formation of the solar system.
You also mentioned before that before going to or selecting the different asteroids to get the samples back, astrophysicists and the scientists did a lot of work in understanding the asteroid itself, also by remote sensing. Is it right? So what kind of technique is this?
So remote sensing techniques is all the technique we can use to study an object without being on the object. For example, we can use radar techniques to study the topology of an object. We can use, to study the composition, the main technique we use is spectroscopy. So for spectroscopy, how it works is that we study the light of the sun that is reflected by the object. However, since the molecules composing the object are absorbing a part of the light to vibrate, we won't have all the light that reach the asteroid. And in the spectra, we will see, for example, absorption bands that are bands that are linked to the nature of the molecules of the surface. So by studying those absorption bands, we can know the composition of the object, for example.
Mm-hmm. And now I have a question about weather, space weather. So we know that space weather can affect the surface of asteroids. And I wonder how much or at what happens. And also then, for example, with a sample return mission, if they, I don't know, do they drill, or how, when they collect the sample, do they just scratch the surface? Do they collect the samples from the surface where it's affected by the space weather effects, or do they have to go deeper to collect more unaffected material?
So that's a very interesting question. Space weathering is a process that combines different aspects. It combines the impact of micrometeorites, also the irradiation from the cosmic rays, and the irradiation from the solar wind. Since the asteroid doesn't have any atmosphere to protect the surface from these energetic particles, there is a weathering of the surface. Only a very thin layer of the surface is affected. It's like taking a sunburn when you go on the beach without a sunscreen. You get red, but your skin is still supposed to be white. It's just like the first layer of skin that becomes red. But the issue is that even if it only affects a thin layer of the surface and not the composition of the asteroid, it has an effect on the spectra. And we were talking about remote sensing spectroscopy of asteroid, but when we look at a spectra of an asteroid, we can see the effect of space weathering. For example, if you compare a young crater and an old surface, you will see that the spectra change. So this is an issue because we use spectroscopy to understand the composition, to determine the composition of this object. And space weathering introduced a bias in the determination of the composition. To our samples that are not affected by space weathering, the two sample return mission adopted two strategies. So the Hayabusa 2 mission did a very, very amazing thing. So I mentioned they collected samples 2 times. How did the spacecraft collected samples? Basically, it was not touching the surface. It was shooting a bullet at the surface. The bullet was ejecting some materials, and they were collecting those ejected materials in a horn. Because they didn't want to touch the surface. If you touch the surface, then there might be a risk that the spacecraft stay stuck. So they didn't want to have this issue. And what they did the second collection, they shot at the surface of asteroids. We know that they collected both the thin layer, space weathered, and also a bit that was underneath. But they wanted to do a second collection with ensuring that they were only collecting subsurface material. So what they did is that they dropped an impactor at the surface. The impactor created an artificial crater, and they went into the ejecta of this crater. The ejecta are basically fresh material that originates from the subsurface. And they did the second collection the same way as the first, by shooting a bullet, but in this fresh material. Like that, they could be sure that the proportion of weathered grains on the second collection sites was very limited. The Bennu collection for the OSIRIS-REx mission, they only did one collection, not two, but to collect the samples, they did a touch and go technique, which means that they went on the surface this time for a very short amount of time, and they went back, and they took samples that are deep enough. So again, they brought back exposed samples and unexposed samples that were deeper that were deeper than the weathered layers. However, the issue is that since there is only one collection, it's difficult now to say this one was at the surface and this one was initially under the surface. It's maybe we will be able to see it by doing some techniques, because we know, especially thanks to the Hayabusa 2 mission, we know what textures are produced by space weathering, but to select them, it's by chance. Before doing the analysis, we cannot really know if this grain will be space weathered and this one no. We have to analyze them to discover that, to determine that.
So since we are speaking about Hayabusa 2 and OSIRIS-REx, I was wondering, what are the major sample collecting missions that are planned for the future?
There are no project of sample return mission from other primitive asteroids for now. However, JAXA should launch, I think, next year the MMX mission. And this mission will study and collect samples from one of the moons of Mars. I think it's Deimos. And this is the next target for the sample return mission. So it's not an asteroid this time, it's a moon of Mars, because scientists don't really know how the two moons of Mars were formed. If it was an object that was captured or a big impact that hit Mars and the fragments reaccumulated, reaccreted to form moons. We don't really know which scenario is correct, so this mission will try to answer this question. But concerning the asteroid, there are missions planned, even if they are not sample return mission. For example, at IAC, the scientific are involved in the ERA mission. I'm not personally involved, but other people from the team are. Julia de Leon, for example. And this is a ESA mission. And the idea is to go back on the Didymos-Dimorphos system. So this is two asteroids, one smaller that is orbiting around the other one. And a few years ago, there was a mission from NASA called DARTS. The idea of this mission is very it's very fun for me because it looks like an American movie. You take a spacecraft and you shoot the spacecraft at the surface of the asteroid, basically. And the idea was to see if it was possible to deflect the trajectory of the small moon by shooting something at it. So they shoot the spacecraft. And the ERA mission is going back to this system to study the effects of this deflection. Because the deflection was successful, the period of time changed, and they want to understand this effect. And this has applications for planetary defense. The idea is to understand if one day a small object comes very close to the Earth, if there is a way to deflect its trajectory. Yeah, so a lot of interesting missions are still ongoing on asteroids.
Yeah,
Agree.
I agree that it does sound like a scenario for a movie. Yeah, so speaking about this topic, so recently, at least in Slovenian news, there have again been some reports about possible collision of asteroid and so on. And so I wonder, of course, we know that it's not impossible because, of course, there's been a big, probably comet or something that caused the extinction of dinosaurs. So things do happen, but yet it's not that likely. So, what's your opinion about this? What are the what is the likelihood of such impacts? How should we understand such news? Every year there's some news. Oh, asteroid impact. Blah blah blah.
Yes, indeed. Sometimes some papers like to be very dramatic about these objects that are passing close to the Earth. They are not that close. Of course, the impact that was responsible for the dinosaur extinction was very huge and exceptional due to the size of the object. It's very unlikely that an impact like that will happen in the next centuries. However, scientists are really involved in the monitoring of smaller objects because you could imagine a small asteroid, a few kilometers in size. It won't destroy an entire planet. However, it could represent a risk for a city, for example. So the astronomers are really studying them. Planetary defense is a serious topic. And they want to understand their trajectory, but also their size and their composition, all the information that are needed to evaluate the risks. And eventually, if one day one of those objects represents a threat for a city, for example, they want to be able to evaluate the risk a long time before, in order to find solutions to evacuate a city, for example, if a city can be impacted by this object. So yeah, planetary defense is a very active field of research, but it's a little bit less dramatic than, oh, this asteroid might impact Earth in 2 years, or I don't know, those kind of titles.
Yeah, we hear this all the time and nothing happens. So there's no reason to panic. Tania, thank you. We came to the end with our questions. We learned a lot. Thank you very much. And yeah, as I said, it's been very, very exciting to speak with somebody who firsthand saw all these sample return, these samples, and who's studying this. And it's been a pleasure to hear results firsthand from you. Thank you.
Well, thank you for inviting me. It was really, really nice for me and very interesting to explain my science. And yeah, thank you for that.
Letošnji marec je minil v znamenju nestabilnega vremena. V prejšnji epizodi sva napovedali 2 dogodka v marcu, in sicer lunin mrk, ki naj bi ga opazovali 14. marca zjutraj, in pa delni sončev mrk, ki naj bi bil viden 29. marca. Žal vreme, vsaj v naših krajih, ni prizaneslo in smo lahko dogodek spremljali na spletu, naprimer, ali pa pregledovali slike drugih, ki so bili pri tem srečnejši. Vsekakor pa upava, da bo aprilsko vreme nekoliko bolj stabilno. Konec marca smo tudi premaknili urine kazalce in torej prišli v poletni čas. To pa za nas, ki opazujemo nočno nebo, pomeni, da nastopi mrak nekoliko kasneje. Aprila meseca bosta izmed planetov še vedno ugodna za opazovanje Jupiter in Mars. Mars lahko opazujemo večji del noči, Jupiter pa nas spremlja le v prvem delu noči. Venera je v tem obdobju danica, torej vidna na jutranjem nebu, in Saturn bo pa šele konec meseca aprila viden na vzhodnem delu neba ob zori. Poleg raznih prizorov, kjer lahko na primer spremljamo, kako se v zaporednih dneh Luna pomika po nebu med ozvezdji, pa je eden manj običajnih dogodkov povezan s planetom Mars. Poleg raznih prizorov, kjer lahko na primer spremljamo, kako se v zaporednih dneh Luna pomika po nebu med ozvezdji, pa je eden manj običajnih prizorov povezan s planetom Mars. Na začetku meseca maja, točneje med 3. in 6. majem, se bo Mars pomikal čez območje, ki ga na nebu zaseda razsuta kopica jasli. Razsuta kopica je skupina mladih zvezd, ki so se hkrati rodile, vendar med njimi ni dovolj privlaka in se bodo v 100 milijonih let porazgubile. Da ne bo pomote, seveda, Mars je samo navidezno na tistem delu neba, ki ga zaseda razsuta kopica. Razsuta kopica jasli se nahaja v ozvezdju Raka. V zapiskih epizode najdete med drugim povezavo do knjige Glej zvezde, v kateri je opis različnih prizorov, ki jih lahko s prostimi očmi ali pa z enostavno opremo opazujete čez leto. Ravno tako sva med povezave dodali aplikacije, ki vam lahko služijo za razpoznavanje ozvezdij in svetlejših teles na nebu. Med drugim najdete pa tudi še spletne povezave za spremljanje preletov mednarodne vesoljske postaje in vesoljskega vremena ter sončeve aktivnosti. Skratka, obilico različnih povezav sva dodali torej med zapiske, dajte si jih torej pogledati.
Kdor želi, lahko z nama vstopi v stik preko e-maila podcast, pisano s k-jem, _temnastranlune@gmail.com ali pa na družbenih omrežjih, kjer naj najdete z uporabniškim imenom Temna stran Lune.
Naj se zahvaliva tudi vsem, ki ste in ki boste s svojimi prispevki tudi podpirali podcast. Prispevek nama lahko ponudite v obliki simbolične kave na spletni strani ko-fi.com / Temna stran Lune in na ta način podprete najino delo oziroma nakup mogoče novega mikrofona ali pa novih slušal.
Podcast je del mreže aktivnosti Zavoda Kozmolab, ki se ukvarja s promocijo in popularizacijo astrofizike. Na spletni strani cosmolab.si najdete povezave do portalov Vesolje in podcasta, kjer objavljamo novice in še marsikaj drugega.
Za glasbeni uvod in glasbeni zaključek epizode se zahvaljujeva Pediju, ki je eden izmed članov trojice, ki ustvarja podcast Opravičujemo se za vse nevšečnosti. To je podcast o življenju, vesolju in sploh vsem, ki ga ustvarjajo Peli, Aljo in Zi.
Če vam je bila ta epizoda všeč, vas vabiva, da se nama pridružite naslednji prvi ponedeljek v mesecu. Z vami sva bili
Dunja
in Maruša. Se slišimo!